All right, good afternoon, everyone. Once again, welcome to today's presentation, where we will be listening to Professor Howard Njoku from the University of Nigeria, Nsukka, where he will be taking us through the webinar title From Stress to Stability, Sustainable Thermal Pathways for Microgrid Resilience. And this is part of our monthly webinar series in the Circular Economy Powered Renewable Energy Center. And if it's your first webinar, basically we are a multi-country, multidisciplinary center advancing knowledge in transition to renewable energy. We're doing this by leveraging the principle of circular economy to achieve this. And this presentation today is part of it just shows some of the progress we've made in work package 3 of our work, and some of the future things we'll do. So once again, thank you for joining, and I'll hand over to Professor Njoku for his presentation.
Okay, thank you, Professor Muiwa. As Professor Muiwa has introduced, I'm Professor Howard Njoku at the University of Nigeria, Nsukka, and I co-lead the work package 3 of the CEPREC project. The webinar this afternoon, or whatever time it is where you are, is titled From Stress to Stability, Sustainable Thermal Pathways for Microgrid Resilience. And in this presentation, we will briefly look at the Africa energy access context, the context behind the CEPREC project. We'll give an overview of the project, and then we will describe approaches to managing loads in microgrids through thermal means. And then we'll look at one case study, one device that's we're developing under work package 3 of the CEPREC project. And then we'll highlight a few things to come in the project and give an outlook of what our expectations are in the work package. The energy deficit in Africa is very well, it has been very well spoken about. It remains a challenge to grant access to most of Africa's 1.5 billion inhabitants, and Nigeria contributes the largest share of the more than 600 million people who lack access to electricity on the continent. So, and this deficit of energy access has led to a lot of economic losses. Productivity is stifled, growth is stifled, and there is a shortage of job creation opportunities. There are challenges related to water supply due to lack of access to energy. Water supply requires energy for pumping, purification, and distribution. A lot of strain is also put on the environment through the reliance on diesel generators and fossil fuel generators generally. So there's a huge carbon footprint and pollution of the environment due to reliance on these fossil fuel sources. The energy access deficit has also led to limitations in healthcare. There is such a supply of power for equipment, medicine storage, and emergency services. There is disruption in education. Many schools lack access to ICT facilities and still lag behind in modern methods of teaching and learning. And again, in the agri sphere, a lot of losses are incurred after harvest due to lack of storage facilities or power for powering storage facilities. And a loss of capacity due to lack of power for irrigation. So this, in a nutshell, seeks to somehow summarizes what the scenario is due to the deficit of access to energy on the continent. Now, the images we have before us show on the left, it shows the level of access in different countries. So the level of lack of access. So north of the Sahara, most of the countries there have almost 100% access. So Algeria, Egypt, population of access virtually 0%. Down to South Africa, where you have just about 14% without access. Then you have countries in the middle, like Chad, with 88% without access. DR Congo up to 79 without access. Then you have Nigeria with 45.
Sorry. I think we all have the same issue. Someone has just
Yeah.
put in the text. We're seeing I think what will happen is maybe, Nitika, are you able to help us share the slides? And if you just see next slide, because we're seeing the previous slide. So we're seeing Africa energy access deficit now. So it's
Okay, you're not
usually
seeing
a
the next
slide
slide.
behind. Yeah, so maybe, is it okay? Nitika, are you able to share the slide so
Sure.
that we can?
Yeah.
Yeah, so if you stop sharing and then just turn your camera.
Okay.
Yeah.
Okay,
You
so
just
have you
stop
sent the
sharing.
slide? Okay.
Yeah, she will present it now.
I've got the slides,
Okay.
yeah. Just 1 minute, I'll share my screen.
Okay.
Okay, can you see my screen okay?
Yes.
Okay. Can you remind me which slide we were on?
Was now on the third slide, even though, yeah, well, I'm on the third slide that shows the map.
This one?
No, that's the first one. The next one, yeah. Okay, so I was going to highlight the scenario in Nigeria. No, the previous slide, please.
Okay.
So I
This
think the
one?
one with the map.
Yeah, this one? I've got the map
No,
on
the one with the map.
Yes.
continent-wide access scenario.
Yes.
Okay.
Okay, so I was going to highlight the situation in Nigeria, where just about 45% of the population lacks access to electricity. But access to electricity doesn't equate to reliability of access. So if you look at the bar charts on the right, you will see that in Nigeria, 16% have no grid access at all. And of the rest that have access, 66 or 60%, they do not have access for most of the time. So this is just highlighting the fact that, yes, you may be connected to the grid, but for some, most of the time, the grid is not working. And so, next slide. So these situations form the background for the CEPREC project. Next slide. Are you on the next slide? So, and the aim of the project is to integrate circular economy principles into microgrids in Africa for sustainable energy transitions. And the key focus of the CEPREC project is the proposal of live EV components for using microgrids. The work package 3 is one of the work packages in the CEPREC project, and the aim is to promote the adoption of solar thermal technologies for low temperature applications to reduce microgrid loads and promote sustainability. So that's the overarching aim. The intended outcome of the work package 3 is the adoption of cost-effective solar thermal solutions, and the intended output ultimately is for solar thermal solutions to reduce the demands on microgrids. Next slide. So we have to answer the question, why loads on microgrids need to be managed. So first of all, when we talk about microgrid load management, we're talking about intelligent control of energy consumption in order to balance the supply of energy with real-time demands of the load. So there's a need to balance supply of energy with demand for loads. And this is necessary in the kinds of microgrids we are dealing with because the energy source is inherently unpredictable. So when you have renewable resources such as solar or wind, they are inherently predictable. They fluctuate all the time. So there's a need to manage the microgrids that depend on them. There's also a need for system stability and to maintain power quality so that the system doesn't degrade, leading to ultimate power loss. So you don't want the fluctuations to degrade the system to the point that a critical loads are left without power supply. And finally, there's need for microgrid load management to reduce the reliance on backups, because with reliance on backups, the problem of greenhouse gas emissions resurfaces again. Next slide. Okay, so now why do thermal loads matter in microgrids? So in microgrids, thermal loads are necessary for supplying clean water. They're required in refrigeration and cooling, and indoor comfort, so refrigeration, air conditioning. These are all thermal loads, and these are vital loads on any microgrid. Sorry, are you on the next slide now? On the slide, the pie chart. And if you look at the pie chart on the right, you will see that most of the loads, the majority of the loads on a microgrid are of a thermal nature. So whether it is heating and cooling, this is a typical distribution of loads on a microgrid. So whether it is heating and cooling, which takes the largest chunk, or whether it's water heating, whether it's refrigeration or cooking. So these are all thermal loads, and in what I have before me, these amount to more than close to 80% of the loads, typical loads on a microgrid. Next slide. Next slide. I hope I'm still connected. Next slide.
Sorry, I think there's a delay on your own side. We are seeing the next slide. Yeah, so what?
Okay,
Just see the name of this name of the slide you want.
Fine. So I'm on the slide with thermal strategies for microgrid load management. Okay,
Yeah,
if you are there now, so
yeah, we're there. Carry on.
okay, so yeah, so I'll be discussing 4 key thermal approaches to managing loads on a microgrid. So the first will be peak load shaving and shifting. Those are actually 2 in 1. Then the next is demand avoidance, which we are very much interested in the work package 3. Then the hybridization of microgrid components, and then the integration of circular economy principles. So now, so the loads on a microgrid look like what you have on the next slide, please. So that's peak shaving and low shifting.
Carry on, we can see it.
Okay. So the loads on the microgrid look like what I have on the left here. So you have those 2 peaks. So those 2 peaks could be in the morning when there is need for water heating, and then in the evening when cooking goes on and then water heating again, and maybe indoor air conditioning. So at those times, there is a peak demand on a microgrid. So one way of managing loads on a microgrid is what is called peak shaving. So in peak shaving, the maximum power demand during peak consumption is eliminated. So you see on the right, you see that those peaks have been shaved off, in quotes, and then the entire load on the microgrid is ultimately reduced. So the benefit of this is that stresses on microgrids are mitigated, and because the total load on the grid is reduced, this also leads to cost reductions. Next slide. So an example of a thermal strategy for implementing this will be the use of thermal energy storage. So if a thermal energy store is charged now not with power from the microgrid, but charged with solar energy directly. Now, during the peak periods of demand, those thermal loads can be supplied from the stored thermal energy. So in this case, that load is removed from the microgrid. Next slide. Now, in load shifting, the peak loads are moved from one time of the day to another. So if you see what I have on the image on the left, you see that the peaks are moved into the so-called valleys. So the load on the microgrid is imposed away from the peak demand periods. In load shifting, the total load on the microgrid is may ultimately not be reduced. So the total load may remain the same, but the peaks in the demand are eliminated, and those peaks are supplied at some other time of the day. The benefit of this is that mismatches between energy demand and supply are overcome. So for example, on a microgrid that depends on solar PV, the peak supply may be occurring at noon and about noon, whereas the peak demands are occurring early in the morning and late in the evening. But with load shifting, that mismatch is overcome. And excess energy generated can be absorbed and not wasted. And the system operation is optimized. So those are benefits. So an example of a thermal strategy that implements this will also involve thermal storage. Next slide. So that thermal load can be moved to periods of peak sunshine. So with thermal storage, the solar energy available at noon can be used to charge a thermal store. And this is charged from the microgrid and used to supply a load at evening peak period, so that at that evening peak period, the load doesn't draw from the microgrid directly, but now draws from the energy that has been stored at noon. So that's an example of an implementation. Okay, next slide. The next slide is on demand avoidance. So in demand avoidance, so this is very simple and also mimics what we mentioned earlier on with peak shaving. With demand avoidance, solar thermal technologies can be deployed to replace electricity-based ones. So, power is not drawn from the micro, it's a thermal load. So for example, why use, next slide, electric heating when you could use solar water heaters or solar distillation? So why use ACs, mechanical air conditioners, instead of passive devices for indoor comfort? So when solar thermal devices are used in place of electricity-driven ones, then we're implementing load avoidance. And this is a very effective and a very powerful means of managing microgrids. So the benefits of this is that significant loads, the significant loads we saw earlier on are completely eliminated from the microgrids. This also enables us to run microgrids efficiently at a smaller size and deploy them at a lower cost. And ultimately, reliability and resilience is improved. Next slide. So a further means of managing microgrids by thermal means is by hybridization of the components of the microgrid. So for example, I'm on the next slide now. The next slide is on microgrid components hybridization. Okay, so in hybridization, the microgrid components are deployed to fulfill dual purposes. So instead of a component to just be generating heat, electricity, for example, yes, it could generate both electricity and heat. And the benefit of this is that redundancies are reduced. For example, in solar PV modules, just about 25% of the solar radiation that falls on the module is converted to electricity. The remaining 75% is wasted as heat. Now, when a PV module is deployed as a PVT module instead, some of that heat that would have been wasted can be recovered so that you have a hybrid PVT cogeneration that generates both electricity and heat. So another thermal-based implementation of this hybridization is the linking of both thermal generators, thermal storages with the electrical components in a single energy management system. So when the energy management system controls both electrical devices and thermal devices, that's a very powerful example of microgrid component hybridization. Next slide. Okay, so the final strategy we will mention has to do with circular economy integration, and this will involve the reuse of waste heat in microgrids in order to reduce reliance on virgin sources. So when waste heat is reused, then there'll be no need to rely on, say, backup generators or the direct use of power from the microgrid to supply thermal loads. Now, when also thermal wastes are converted into useful energy forms, so these add value and enhance energy security in a microgrid. So I think let's go to the next slide. So these strategies are the concern of work package 3 in the CEPREC project. And then the work package 3 is concerned with solar water distillation and pasteurization. That is the work that is being done by myself here at UNN and Dr. Stan Sher at Warwick, and the solar-driven cooling, which is being carried out by Dr. Peter Kumani at the University of Nairobi. We are also interested in solar heating and drying, even though no work on that has begun yet. And all these technologies are geared towards load avoidance. You will remember that one of the strategies I mentioned for managing loads in microgrids through the thermal means, one of them is demand avoidance. So by developing these solar thermal-based systems, their deployment will ultimately lead to the avoidance of direct power demands on a microgrid. Next slide. I will speak a little more in detail about the case study on solar water distillation and describe some innovations that we are trying to implement related to this technology. Okay, so clean water, the water energy nexus is very well discussed and has as background to it huge populations that lack access to clean water supply, and the conventional water purification methods require a lot of electricity, both for pumping, for purification, for distribution. Now, currently, in many African societies, communities, there's a lack of safe water in rural households and health facilities. Just as we had discussed earlier on about the lack of energy, there's a connection between the two. Now, if the energy problem is solved through microgrids, that will immediately create a scenario of thermal loads on those microgrids to solve the water problem. So by the work we are doing in this, we are trying to address the two at the same time. Next slide. Now, water purification by solar energy is the most basic implementation of that is the basin water still, which you will see on the right of this slide now. And the operation of the basic water still mimics the hydrological cycle. So sunlight heats up water, the water evaporates, as you can see on the image on the lower right, water evaporates. It condenses on the clear, transparent cover, and then pure water is collected. The operation of this system depends on the temperature difference between the saline water and the condensing surface. So the temperature difference, the more the temperature difference, the more the water that can be drawn from this. The big advantage of this is that this system is very simple to build, very simple to operate. It's a low-cost system, very simple, no moving parts and all that. But the disadvantage it has is that the heat losses in this system are very high. The output is very low. The efficiency of the system is also very low. Now, I have sketched at the top there what happens on the transparent cover. So on that transparent cover, all the incoming solar radiation, most of the incoming solar radiation goes through that cover because the cover is transparent. Now, when the water condenses on the underside of the cover, it releases its heat to that cover, and that heat is dissipated by radiation to the ambient environment and by convection to the ambient environment. This process is not very efficient and ultimately leads to a rise in the temperature of that transparent cover. Next slide. So, okay, I've spoken in more detail about the shortcomings of the solar water distillation system here, so I won't repeat this. Next slide. So, because the CEPREC project is also very concerned about delivery on innovation, one of the things we are doing is to develop an innovative improvement on the basin type solar steel I just described now. And this involves the hybridization of a basin type solar steel with a shallow solar pond. So the protrusion you see on the left, on the image on the left, the left image is a shallow solar pond, which is a very efficient device for collecting solar heat. So this device can collect solar heat with efficiencies going close to 80%. So it's a very efficient system. Now, coupling this with a basin type solar steel presents us with the possibility of harvesting clean water more efficiently than could be done with the basin type solar steel. The parts of this device are listed here. For time's sake, I won't be going through them one by one. So, but how this operates, the solar radiation heats up water in the shallow solar pond. The heated water rises into the the basin into the solar steel compartment. It evaporates there and condenses on an opaque surface. Now, that opaque surface I have enlarged above so that you see what is going on. That opaque surface is made up of two layers. The first layer below is opaque but reflective. So that's the gray layer you see there is opaque but reflective. So all the solar radiation enters through the solar pond. No solar radiation enters through the condensing surface. Now, so when the solar radiation, so it's a double layer. So the lower layer is reflective. The upper layer is transparent, but it's transparent to short wavelength radiation. So when radiation comes, it goes through it. It hits the lower opaque layer and is reflected. So whatever solar radiation falls on that surface is reflected. Not much of it is absorbed. Now, however, that upper layer is also emissive, but it is emissive in what is called the atmospheric window. I have tried very hard to make this as simple as possible so that the diverse audiences in this webinar can follow what I'm describing. So common surfaces are emit. The emission of common surfaces can be approximated to gray emission. So that means that the emissivities are constant across the entire spectrum. However, some surfaces are selective. So, and that's the kind of surface we have there. So this surface is highly emissive in the long wavelength band, but it's highly is highly reflective is transparent actually in the short wavelength band. So because it's transparent in the short wavelength band, you see that the incoming short wavelength radiation, that's the yellow arrow, goes through that first layer and reflects through the first layer. However, when the vapor condenses on the lower layer and releases heat to the lower layer, that upper layer emits it and emits it through the atmospheric window. The atmospheric window is a wavelength band within which the atmosphere, that's the sky, allows thermal radiation to pass through into space. So effectively, this allows this system to exchange heat with space, which is at close to 0 Kelvin. Okay, so that's it. So close to 0 Kelvin. So now the effect of this is that the temperature difference I talked about earlier on, the temperature difference between the condensing surface and the water that is evaporating, the temperature difference is increased greatly and water collection is improved. Okay, so this hybrid system will eliminate shadows and wall losses. And so a few other innovations we'll be considering will be the use of bio-based evaporators to enhance evaporation. I've talked about the spectrally selective coating to improve the condensation. We'll also be implementing phase change material storage, latent heat storage, to extend the operation of this system beyond sunshine periods. So these are the innovations that we'll be exploring in this device. Next slide. Okay, so this is an exploded view of the device. You will see immediately that the simplicity of the basic basin type solar steel is not compromised. So the novel hybrid steel we are proposing retains most of the simplicity of the basin type steel. And so that enables it to remain a low cost system that will be affordable and accessible to rural households and the kinds of households that we are targeting in Africa. So this device will be adaptable and also very find much use in healthcare facilities and rural households. And I've talked about extending the operation beyond sunshine periods to facilitate both peak shaving and low shifting which we had discussed earlier on. Okay, next slide. So what are the expected impacts of this system? This system will support reliable clean water for healthcare facilities and homes. It will achieve microgrid load demand avoidance, which we mentioned earlier on. And because it depends entirely on direct solar radiation, there'll be no need for electric boiling. And by integrating thermal technologies in the circular microgrid frameworks, this will strengthen overall circular economy principles. Okay, so as I wind down, so these are the next steps in the work package 3 of the CEPREC project. Next slide. So what is ongoing currently is the prototype development of this system, which is at an advanced stage, and the thermal modeling. So as is necessary for developments like this, they need to model this system and investigate its operation in different scenarios. And so this is going on at an advanced stage currently. And going forward, the system is going to be tested in outdoor conditions to investigate heat retention, distillate yield, system efficiency in real life operating conditions, and also assess the effectiveness of the system for demand avoidance, as we have described earlier on. Next slide. So ultimately, these are the expected outcomes from work package 3 on this particular device. And now, time constraints do not allow us to deal with all the devices I mentioned earlier on. So the discussion has dwelt largely on just one. So, and ultimately, we're expecting a modular low-cost solar steel design that will be suitable for local fabrication and scaling in African context. Useful for reducing microgrid load by load avoidance, offering reliable access to clean water for rural households and healthcare facilities, and able to operate beyond daylight periods through the use of VCM storage. So this will ultimately contribute to the SDG goals that I've listed here. SDG 3 on good health and well-being, SDG 6 on clean water and sanitation, SDG 7 on affordable and clean energy, SDG 12 on responsible consumption and production, and SDG 13 on climate action. Okay, so that's the key takeaway. Thermal load management strategies, load shaving, load shifting, load avoidance, hybridization, as the backbone of resilient, sustainable microgrids. These are the backbone of resilient, sustainable microgrids. And then in work package 3, we demonstrate these via solar, distillation, heating, and cooling. Okay, so thanks for listening. I'm on the very last slide now. Thanks for listening. Okay, I hope they will have just enough time to receive questions.
Yes, we have a bit of time. Thank you very much, Professor Njoku.
Thank you.
Yeah, so now the floor is open for questions. So if you have any question, if you just raise your hand and I'll give you the ability to speak. Any questions? Okay, so I have Modi. I've allowed you so you can speak.
All right, thank you, Muyu. Thank you, Prof, for such a wonderful presentation. My question is, for all of these designs, which one of them would you say is closest to market, so that we can look into adopting them as soon as possible? Thank you.
Close to market. So these are these are new designs that are just being developed. So actually, when I talked about the next steps were about proving the concept. So they are still far from markets at this stage, but the technology, the science behind them is very solid, and we expect that they will advance through the development cycles very quickly.
Okay, thank you, sir.
I see Osita's hand is raised.
Sorry, Osita. I was muted.
Okay, thank you, Prof, for the good presentation. One of the questions I have is, I can see that the major source of energy for your device, especially the distillation device, is water distillation device is solar. Do you
Yes.
consider any other source, any other renewable energy source other than solar? And another question is the efficiency of your device during a period when we have more sunshine, maybe during a rainy season, cold weather or thereabouts. When the solar output is low, what alternative do you have in mind to reduce the stress, the low stress on microgrids? Thank you.
Okay. Okay. Thank you, Dr. Major, for that very interesting question. So you may recall that while I made the presentation, I mentioned the fact that we intend to explore phase change latent heat storage in order to extend the system's operation time. So with phase change heat storage, it will be possible to operate this system beyond sunshine periods. So the basic basin type solar steel only operates during daytime and just a short while after that. Now, when you incorporate thermal storage, you are able to extend the operation time of these systems virtually 24 hours. So if you had sunshine at the appropriate time. Now, but of course, like your question highlighted, there could be periods of extended absence of sunshine. So maybe you had maybe bad weather for a couple of days or something like that. Yeah. So in principle, this device you should be able to also run on electricity. So if you had it coupled to an electrical source, but that is what we want to avoid. So, but at this stage, it should be able to run continuously based on the PCM storage, which we intend to incorporate. We will achieve the proof of concept at this stage. Going forward, we can now specify more stringent expectations from the device here. I hope my answer satisfies your question.
Yeah, thank you, bro. Yeah, thank you.
Okay, thank you. Iata?
Okay, yeah. Thank you very much, Prof, for the presentation. I was just thinking if some of these technologies that you presented are being considered as productive use equipment to be used with the microgrids, and if maybe some analysis on their revenue potential is being explored, if there could be productive use equipments with microgrids.
Okay, thank you very much for that very important insight. Ultimately, it essentially produces clean water. So it's basically productive. Now, the economics of the water produced. Okay, so because of our backgrounds, that's not usually a first consideration, but it's a very important consideration. And I will count this to be a suggestion that we will tinker on and incorporate into what we plan to do going forward. So I'm very grateful for these insights. We'll incorporate it into what we are doing.
Thank you, Prof.
Thank you very much.
Okay, so we have Modi again.
So Prof, is it possible to up the scale in terms of the technologies to go towards concentrated solar power, for instance? Because as you would know, that is much bigger than PVs, while microgrids have their problems, including sustainability, because of course you have DFIs having to bail out customers. I am a strong believer of scale. So CSPs perhaps could be an area to look at. So is it possible to include CSP on a larger scale for these technologies you're looking at? Because of course, like you said, you're looking at proof of concept. So I guess my question is, have you looked at CSPs, or would CSPs be something you would consider to look at? Because of course, Nigeria has a lot of solar irradiation. Why not just go big instead of saying small, And with energy systems, the larger the scale, the better the economics anyway, to piggyback on the last question. Thank you.
Yes, thank you very much. Okay, so because of the nature of this presentation, of course, there were limitations on what could have been presented, but your question draws me into also discussing this also. So the solar steel works on two principles. So there's a source and there's a sink. The source is solar power. Now there is the need for a sink where the heat released by the condensing vapor is discharged into. So in the common solar steels, that sink is the ambient environment. The ambient environment is at say 30 degrees, 25 degrees, 35 degrees. So within 25 or 35 degrees, depending on where you are. And that sink is a huge limitation. So the key innovation in the solar steel that we are trying to prove here, whose concept we're trying to prove here, is that it works with a sink that is at a temperature close to absolute zero. So it's exchanging heat with space. So at about 40 Kelvin. Now, if there will be a need for concentration, what we are tinkering with is concentrating the exchange of heat between this device and space, concentrating that heat exchange at the sink side, not at the source side. When you have CSP and all the common terrestrial concentrating systems, the concentration is happening at the source side. Now that is good. That's what it can be, because those devices do not actually require a sink. The sink side is not critical to the operation of those systems, but that is what it is in this one. So going forward it's on our list on the things to investigate, but the concentration we are interested in is not on the source side. It's not on concentrate the amount of heat that comes in because of the nature of solar distillation systems, but on concentrating the ejection of heat on the achieve that, then the amount of clean purified water you are able to harvest also increases, in a very significant manner.
Right. Thank you, Prof.
Thank you very much. Thank you very much for that consideration you brought in.
Okay, thank you. So we'll go next to some Tochukwu.
Okay, thank you, Muyiwa. Thank you, Prof, for the wonderful presentation, as always. Okay, so my question will be around yes, sir. So my question will be around the proposed timelines. So I was thinking, is there any timeline for this proof of concept stage to be completed? That is my question, sir.
Okay, so the CEPREC project has a 3-year timeline beginning 2025 and ending by the end of 2027. So like I presented in the, I think this is sufficient time to complete the proof of concept studies we are doing. And like I presented like I showed in the presentation, we have advanced with the development of the prototype. We expect that the testing will begin before the end of this year. So we have sufficient time. Yeah, we have sufficient time to prove this concept. And we are expecting that maybe in a future presentation like this, we should be able to show the kinds of results that we have seen on the field.
All right, sir. Thank you.
Thank you very much.
Mod, is that a legacy hand or you have another question?
Yeah, just last points. So, Prof, when you discuss about the source of it and collecting concentrated energy, I have a suggestion to make. Is it possible to? I would like for you to consider adding molten salts, if possible, to get as much temperature as possible to store that heat for other productive uses as well. If that is then considered into a prototype or demonstration plant, that would allow other researchers, I mean, like myself, I've picked interest from this, to come over to perhaps test it for other productive uses and potentially replicate it in other places around the country. So I guess my suggestion one is to consider having molten salts added, at least even if it's on the design phase where we're collecting those concentrated energies. And if that works and passes the proof of concept stage and budget allows, it would be lovely to have that as part of a demonstration plan so that we can come visit if the opportunity presents itself. Thank you.
Thank you very much. And thank you very much for that suggestion on the use of molten salts. I understand this to be the use of molten salts as the phase change material. So thank you for that suggestion, and we'll surely consider it. One big part of the project is on the incorporation of phase change materials, and we'll surely consider the suitability of molten salts and implement it in what we are doing. Yeah. Thank you very much. Thank you very much for that suggestion.
Okay, thank you. Thank you all. I see a question about the slides. I'll have to see how we can do that, but just to note that is the webinar is recorded and it will be on our YouTube channel. And if there's a way we can put somewhere to download the slides, we don't have a problem with that. We can send it by email. But yeah, I'll look at that and see how we can actualize that. But what we do usually is to have the webinar recorded, uploaded to our YouTube channel. So I've just sent a link to that where you can link tree where you can find our YouTube channel and see previous webinars covering different things. And just want to say thank you to all of you for joining, and thank you very much to Professor Howard Njoku for presenting this webinar. I think this is our fourth or fifth webinar.
Thank you.
So yeah,
thank you, Prof,
we
for having me.
Yeah, we look forward to having you on our next webinars. It's usually first Wednesday of the month, so the next one will be in November. All right then. Enjoy the rest of your week.
Thank you, and bye, everyone.